So I welcome everyone for the last colloquium of January. Next week, there's no colloquium. So it's a pleasure to welcome one of our own members. And it's always a good thing that when I get interested people wanting to give colloquium, and I'm happy Rishi. We were talking to him quite often for last 6 months. I'm sorry, Rishi, there were some date changes. So I apologize for that. But finally, we are having a colloquium. Rishi comes from the Department of Theoretical Physics, and he has a deep interest in cosmology. But what is interesting to me is Rishi's initial story. Rishi actually did his BTech in electronics engineering from Punjab Engineering College in Chandigarh. And he took up a job after finishing the BTech degree in Texas Instruments, which is a well-known company amongst those who are finishing up electronics degree. Okay, and this used to be well known in my time also, in when people used to graduate from BTech. And working for 4 years in Bangalore, after working for 4 years, Rishi decided this is not exactly what he wants to do, and sort of in 2004 he went to University of Urbana-Champaign, and this is University of Illinois at Urbana-Champaign, UIUC, for his PhD in astrophysics. And that's where he got into cosmology and CMB physics. So this journey began somewhere in 2004. He finished in 2010 his PhD, and then went to Max Planck Institute of Astrophysics in Garching. Yeah, Garching. Okay. And in 2015, he moved back to our institute, and he has been here since. It's almost 10 years now. So, Rishi, I'm glad that I can hear you now finally, a colloquium I didn't hear in my stay here. So, it's great that you are giving a colloquium. Thank you very much, and I welcome you.
Thanks, Jyotishman. So I want to talk about cosmic microwave background and how it tells us what we learn about the universe using the cosmic microwave background. So the picture that you see here, the background picture here, this is actually a picture of sound waves at the time of when universe was going through a phase transition. So it was going from ionized state to a neutral state. The electrons and protons, they were recombining to form hydrogen atoms. And at that time, there were sound waves in the universe. It was full of sound waves. And these are the sound waves, or to be more precise, these are the density fluctuations in the plasma at that time. And and this is basically a superposition of sound waves of many different frequencies that you see in real space. And if you look closely, you will see that there actually features are a particular size. You don't see, features of all sizes, but they have a particular size, which means that the sound waves are peaking at one particular frequency, which is dominant. And if you make the spectrum of these fluctuations, you see that there is indeed one particular frequency which dominates, and this is what you see. So this is about a degree size sound waves, or the that we see today on the sky. So I will talk about, and we'll see that in the spectrum there are many other features, there are many other peaks, and there is a particular pattern to these peaks, and there is a lot of information there in this pattern, and I will try to explain how what is the information that is hidden in this pattern, and what is the physics behind it. So the sound waves is just one aspect of the CMB, one of the most important aspects. The another important aspect of the CMB is that, so this is the spectrum of the spatial anisotropies, or the spatial spectrum. But if you look at the intensity of the CMB as a function of frequency, or the wavelength of the photons that we are observing, and we see that it is actually almost perfect black body spectrum. It is not perfect black body, it is almost perfect black body even in the standard model of cosmology. And in standard model of cosmology, we expect small deviations from a black body spectrum, and that has also important information. And some of those deviations we have measured, others we hope to measure in the future. But if you introduce new physics beyond standard model, then we see that there's an even richer spectrum of deviations from this black body spectrum that we expect. And that has actually even, there's a rich possibilities of what we can learn. So unfortunately, the last experiment that measured this spectrum, so for this spectrum, there have been lots of experiments, starting with the COBE experiment, which was the first one to measure this this imprint of the sound waves. There have been lots of experiments from ground and space, and this is a steady process has been made. But this actually, COBE in 1990s, it measured this this part of this spectrum. But after that, there has not been a new experiment, and we hope that hopefully in near future there will be a new experiment which will also measure this, and we will learn a little bit more about it. So most of the talk I will focus on this part, but hopefully if I don't run out of time, then I will also try to explain some of the physics behind this part also. So over the past 9 years, during different times, this research that I will be presenting, it is sponsored by, of course, by DAE, but also external funds from Max Planck Society and also SERB. Okay, so we want to understand the universe with the cosmic microwave background. But first, I want to start with the something more basic, with this, the discovery of the universe. Before we start studying the universe, we have to discover the universe. And this is actually interesting, quite interesting story. And what I mean by discovery of the universe is there are two facts about the universe. One is that the universe is big. It's really big. So I think if you are a fan of science fiction, then we might have read this book, which is Hitchhiker's Guide to the Galaxy. And this guide explains, if you ask him what is universe, it goes on into a lengthy explanation, starting with that it is really big and how big, and try to give you a feeling of how big it is. That is actually really, really mind-bogglingly big. You would not believe how big it is. And this is an interesting story how we, so this is the first discovery was the scale of the universe, how big actually the universe is. And this was not always the case. So it was actually, so all of these discoveries very interestingly came same time as Einstein's relativity and quantum mechanics, all these theories were developed. At that same time, we were also discovering these basic facts about the universe. So before 20th century, it was thought that the Milky Way, our galaxy, was the whole universe. The building block of the universe was stars, and that the stars that we see in the sky, that was the whole universe. It was made of stars. You could see the telescopes were not sensitive enough to resolve the galaxies. So, and we could see galaxies. So there was small Magellanic Cloud and large Magellanic Cloud, which are the nearest galaxies that we can see even with the naked eye. They are in the southern hemisphere. But also the Andromeda galaxy also you can see if you are in a dark part of the sky, but they appeared as clouds. So naked eye, they appear as some clouds in the sky. But and especially Andromeda and other galaxies, they had some spiral structure. So the clouds in the Milky Way were called nebulae, and these clouds were called spiral nebulae. So there was already some discussion about what is the nature of this spiral nebulae, whether there's something special or they are. Most of the clouds are basically just clouds in which the stars are being forming. So starlight lights up the clouds, and we see those gas clouds. So most of the clouds that we see are really gas clouds which are within our galaxy. But some clouds. Like 1900. 1900. So 20th before 1900. So I will come to so here we have some dates. But already in 1750, actually, astronomers were speculating about this nature of whether there may be other systems of stars in the universe. But this was a speculation. They had no data. They were more in philosophy than physics. So Thomas Wright was the first. He actually also the first was, I think, as far as I know, first one to recognize that the reason we see a thick band of stars in the sky is because our system of stars is in the form of a disk, and we are in the disk. So when we look through the disk, we see most of the stars form a band on the night sky. So the disk nature of Milky Way was the first. He also was the first one to speculate that there may be other systems of stars like Milky Way in the sky. And in particular, this philosopher Kant, he also took up this idea and he called them island universes. There may be other island universes. And in particular, by 1900, this was the situation. The best size estimate of the size of the universe was 10 kiloparsec. That was the furthest stars that we could see, and we could estimate their distances too. But while this was going on, actually, the second fact was discovered, which was that the universe is expanding. So this was Slipher. He took the spectrum of the spiral nebulae and measured their Doppler shift. So the spectrum lines were shifted, and he found that actually most of them, they had a positive shift. The velocity was positive, which means they are all positive velocity here means that spiral nebula is moving away from us. Right? So most of them were actually positive. There were few objects which had a negative velocity. They were coming towards us, but most of them were moving away from us. And now we know actually if we look at if we check Wikipedia of these objects which have a negative velocity, they are actually within 1 megaparsec of us. And all the objects which have large velocities, large positive velocities, they are actually at the distances of 10 megaparsec. So Slipher has actually discovering the expansion of the universe already in 1915. But of course, he did not know that because the universe was not discovered yet. So expansion of the universe was discovered before we discovered the universe. It's also interesting here, this is a part from his paper. And here you see that first he took data for some of the objects, and then he found that, okay, there seems to be the signs were all negative on one side of the Milky Way and positive on the other. So it indicated that there was some drift, this nebulae were drifting across the Milky Way. But of course, it went away when he had more galaxies and he got more data, then this drift became insignificant and actually mostly it was expanding. So we are actually seeing some similar kind of drift on the sky. Today also there is a debate, not these objects, but other objects, other galaxies, that whether there is some bulk flow or not. But anyway, so that is a different story. But already here you see that if we get more data, then actually a lot of these anomalies, they come and appear, and usually is the quality of data which is important. So these are coming towards us. So these are close by objects. So they are basically, if the galaxies are close by, they are galaxies which are close to us. They are getting attracted by our own galaxy. So there's a mutual attraction. So the close by galaxies, they move towards each other. So that is why we see. So these are basically one of them is Andromeda, and Andromeda we know it is moving away towards us because we are all in this local group and the galaxies are falling towards each other. But as you go further away, then this effect of the gravity of the nearby objects becomes unimportant, and is the expansion of the universe which takes over.
Hi, just curious why the velocity is shown in units of km.
This was the convention at that time. So per second was assumed. So wherever, so in the old papers, whenever you see kilometer, you assume it is kilometer per second. That was for some reason the convention in astronomy. So even in the Hubble's plots, you will see fewer more plots I see, just kilometers. So everyone knew that per second was implicit. Okay, so in 1920, this situation was there actually until 1920. 1920, there was a great debate on the scale of the universe. This is actually important enough that NASA maintains a special page on it, and you can go to it and actually look at the whole debate. There's a transcript of the debate and what were the arguments. There are also later analysis of the debate. And the debate was between two people, Shapley and Curtis. And Shapley argued that the spiral nebulae that we see, they are just the gas clouds, and the Milky Way is the entire universe. Whereas Curtis argued that spiral nebulae are actually the galaxies like Milky Way, and they are outside the Milky Way. But of course, they could not arrive at a conclusion in this debate in 1920 because to know whether to settle this debate, you have to measure the distances accurately. And that is one of the hardest problems even today, how to measure distances to these external galaxies or on cosmological scales. And the distance measurements at that time were not accurate enough. So if you look at the debate, you will find that actually Curtis is arriving at the right conclusion, but he's actually using the wrong distances and wrong arguments. Shapley has slightly better distances, but he's using again the wrong arguments to arrive at the wrong conclusion. So in any case, so you could, if you don't have data or good enough data, then you can argue all day without arriving at any conclusion. So this is the debate on the scale of the universe. I will later part of the talk, we will see that today we will have a similar debate. We have actually come full circle. But today the debate is not on the scale of the universe, but how fast the universe is expanding. So the resolution of the debate needed accurate way to measure distances. So which means first you have to know what is the scale of the Milky Way, how big the Milky Way actually is. And then you have to know the distance to the spiral nebulae. Then you can show that distances to the spiral nebulae is much bigger than the size of the Milky Way. Then you have proven that these are actually systems which are external to Milky Way. So Leavitt, Henrietta Leavitt in 1912 had already found that there's this particular stars called particular variable stars called Cepheid variables. They are undergoing a radial pulsations. So the star contracts and expands periodically, and as it does so, its luminosity also goes up and down periodically. So you can measure the period of pulsations by just looking at the light curve of the star. And she found that there is a correlation between this light curve and the luminosity, absolute luminosity of the star. So more luminous stars, they have a longer period. So this is, I think, one axis is the log of period, one axis is the luminosity. And so one is the log of period and luminosity, there is a straight line. So there's a correlation. So this is of order days. Yeah, so the period is of order days, I think. Right. So this provided actually, so this meant that we can use this as a standard candle, because if you measure these variable stars close by, and you can measure their distances by parallax, for example, then you can calibrate this relation, the luminosity. If you know the distance by parallax, you know the flux, so you know the luminosity, and you measure the period, you can calibrate this relation. And then you can observe this in a much further away. And then if you measure the period, then you know the luminosity, and you measure the flux, you can get the distance. Right? So this provided a way to use them as standard candle, but no one before Hubble actually. So this was a big contribution of Hubble, that he actually used this. So this is the formula. So if you the flux is what you measure, energy per unit time per unit area falling on our detector. Luminosity is emitted per unit time by the star, and then the energy conservation tells you that this is 1 over r square law. So if you measure the flux and the Cepheid period gives you the luminosity from that relation, and then you can solve for the distance. So Hubble used this. So these stars were already known by this time in the Andromeda galaxy. Right? So Hubble used this relation to measure actually the accurately measure the flux, and then use this relation. He used actually the relation calibrated by Shapley later on after Leavitt to measure these distances. And he showed once and for all that the Andromeda actually much, much further away than any known star in the Milky Way. So it is actually a system external to the galaxy. So he settled. So this part of the debate about the scale of the universe, whether the spiral nebulae are part of Milky Way or there are other galaxies, this was settled in 1924. Then by the Einstein's theory of relativity was already there. So Friedman actually found solution. He wanted to apply these Einstein's equations to the whole universe. And if looked at the simplest models of the universe, perfectly homogeneous and isotropic. And he found that in such a universe, you have solutions which are actually either expanding or contracting. So the universe should either expand or contract. It cannot be static. And then Lemaitre actually, he connected these solutions of Friedman to actually Slipher's measurement of velocities, which showed that galaxies were moving further and further away from us. Or most of the galaxies or spiral galaxies were moving away from us instead of some random velocities. So he connected these two and figured out that, okay, what Slipher was seeing was actually this actual solution of Friedman's solution. The universe actually behaves like what Friedman was predicting. And there's a famous story about how Lemaitre convinced Einstein that to give up his cosmological constant. So there's a story, okay, I have seen, heard many times about Einstein's greatest blunder, that actually his greatest blunder was not putting in cosmological constant. Cosmological constant is perfectly allowed by general relativity. So that is not the blunder part. That is, I think, sometimes misstated. The blunder was that he tried to make the universe static. Whereas if you look at general GR equations, his own equations, and try to make a clear static universe, does not matter how many cosmological constant or what you do, it is impossible. The static universe is unstable. It's an unstable solution. So universe has to be, GR does not allow for a static universe. Universe has to be either expanding or contracting. It has to be dynamic. So that was the Einstein's blunder. And famous story about Lemaitre meeting Einstein and Hubble, and then convincing Einstein to give up the quest for a static solution. Then in 1929, Hubble measured distances to the other galaxies also, many galaxies, and he found what is we know today as a Hubble diagram, that there is a relationship between distance and velocities. So what is that? So this is the Friedman metric. These are solutions that Friedman had found. So this part is basically just the metric of flat. If you k is 0, that is just the usual Euclidean distance, but written in spherical coordinates. This is just dx square plus dy square plus dz square, but I am writing in an r theta phi, the spherical coordinates. K is basically the curvature term. It allows for this space to be curved either positively or negatively. And this A is the scale factor. So this part in the brackets is what I call co-moving coordinates. These are the coordinates I fixed at each point in the universe. And these are the numbers that I fixed, and they don't change as the universe expands. So I have scaled out or factored out the expansion of the universe in the scale factor. Right? And then this is the time part of the four-dimensional metric. So the proper distance, if you want to calculate distance between 2 points with coordinates r, between that is 0 and r, then you multiply this r, the co-moving distance, by the scale factor. And if you take the time derivative of it, the scale factor, that is how you define the Hubble parameter. It's just that how fast the universe is expanding. So it's a time derivative of scale factor. And if you take the time derivative of this relation, the physical distance is scale factor times the co-moving distance. Then you arrive at this relationship that the velocity of the nearby galaxies, that should be linearly proportional to the distance. So further away the galaxy is, the faster it should be moving. And the proportionality constant is called the Hubble constant. And the one over the scale factor is known as the redshift, 1 plus z. Z is the redshift. So if you have a emitter emitting some photons at a particular time, early time, and then we observe it today. So at that time, the scale factor was, let us say, A1. You observe it when the scale factor is A2, and you will see that the wavelength of the photon that you observe is smaller, is bigger than the wavelength that was emitted, or the frequency is smaller by a factor of the scale factor. So that is known as the redshift, that the photons which were emitted when they were blue, today if they observe it late enough, they will actually be in the red part of the spectrum. So that is the redshift. Just the inverse of the scale factor. The ratio of the scale factors between emitter and observer gives you the relationship between the frequencies that you will observe. And this is true for not just massless particles like photons, but all momenta redshift as 1 over A. That is just because the metric of the, or the frame of the reference that you are seeing is evolving, and the energy that you measure is actually a frame dependent quantity. It is not a frame independent quantity. So this is what Hubble measured, that he found that this the relationship which was predicted from the Friedmann solution, that velocity should be proportional to the distance. And this is approximately what he measured. So this is today known as the Hubble law. So now if we extrapolate backwards, we take the expanding universe and we say, okay, what happened in the past? So the past, if you extrapolate backwards, and this is just the adiabatic expansions or contraction. So the energy is conserved, of course. So universe will become denser and denser and hotter in the past. Like photons will have higher and higher energy, and higher, and all the matter will have. This is the distance, and y-axis is the velocity. So again, per second is missing. It is kilometer per second. This is parsecs. 6 or 10 to the power 6 parsecs. This is like a megaparsecs. So this galaxies, the typical distance of galaxies is megaparsecs or 10 megaparsecs. Right, so parsec is around 3.2 light years, and 1 light year is the distance light travels in 1 year. Right, so if you explore backwards and backwards, the universe will become denser and denser and hotter. So at some point, atoms cannot exist because the universe is so hot that atoms should be ionized. If you go even further, even nuclei cannot exist. You should have separate protons and neutrons. If you go even further, you should have quark-gluon plasma, right? So in 1948, Gamow gave this idea that, okay, at early times, we would have protons and neutrons, and then at some point as the universe cools, they will actually combine to form helium. And then to get the right amount of helium that we need, so we have approximately 25% helium, 75% hydrogen. So only 25% of the matter has to go into helium. You cannot put everything into helium. So 75% has to remain hydrogen. So you need very precise conditions, very precise density and temperature, and it is dictated by the lifetime of the neutron. So free neutron is actually unstable. It decays on time scales. With decay lifetime is around 900 seconds. So you have a time limit. So the nucleosynthesis has to happen in a particular time, and then you should have particular temperature and density for this to happen. And then if you measure the density of matter today, then you can calculate what is the factor by which the universe has expanded since BBN until today. You know the temperature of radiation at that time. You can also calculate by what factor the temperature of the radiation would have decreased. And they did this calculation. So Alpha and Gamma Herman actually did the actual calculation based on Gamo's idea. And they predicted that the universe, the radiation should have cooled down to few Kelvin today. This was, I think, the first non-trivial predictions in theoretical cosmology. And this was discovered in 1965. by Penzias and Wilson. So if you keep going backward, at some point you will need infinite density. Actually, you need to reach infinite density in a finite amount of time. So at t equal to 0, so that is the Big Bang. That is what we call the Big Bang, but it's a hypothetical point because we don't have physics which can predict what will happen we don't know what will happen at such high densities. We cannot, our knowledge of particle physics becomes very uncertain these days. Right? So this is like a hypothetical point. If you just extrapolate backward, you at finite time, you reach infinite density. So that we call the origin or the, so that is, we measure all times that I will be measuring. It will be from this, the scale factor goes to 0, time, we choose that as our 0 of our time. Right, so this is the picture of the universe. So by definition, we are at the center of our own observable universe, right? Just the relativity forbids us to be in contact with any space-like event, or that we can only observe our past light cone, right? We cannot observe the three-dimensional universe, or the universe is four-dimensional, 3 dimensions of distance plus 1 dimension of time. We can only observe three-dimensional light cone in our past universe, which means that as we go look further and further, we are also looking at the earlier and earlier time in our universe, right? So in one sense, we are actually, in cosmology, we actually, the whole evolution of the universe since the Big Bang until today, it is actually laid out in front of us. We just have to look further and further away, and we are looking at earlier and earlier stages of the universe. So the earliest we can probe directly is this Big Bang nucleosynthesis, which is, we measure the abundance of elements which are produced. So we know the conditions which were there at this time. So there are 3 axes. So one is the redshift, or the inverse of the scale factor. This is the factor by which the scale of the universe was smaller at that time. This is the temperature scale. The CMB, what was the temperature of the CMB as you go further and further, or earlier times, it becomes hotter and hotter. At some point, I changed from Kelvin to electron volts. And this is the time in years as measured from this hypothetical t equal to 0, which is here. So here t equal to 0 is here. We are at the center, right? And one of the important phase transitions in the universe, which happens is this last scattering surface when the universe goes from ionized to neutral. So this happens when the temperature of the universe is of order few electron volts. So the hydrogen ionization is 13.6 electron volts, but you have to cool it a little bit below that in order for the universe to recombine. So that CMB, so before this, the universe is opaque. So the universe is fully ionized. It is full of free electrons, and they scatter the CMB photons by Thomson scattering or Compton scattering. So the mean free path of the photons is quite small compared to the size of the universe. So photons only move a little bit, and then they scatter off the electron. Right? So in other words, the universe is opaque to the CMB photons. Of course, CMB photons they are not in microwave range at that point. They are optical photons or UV photons. But once the universe recombines, the free electrons disappear. They are bound up in hydrogen atoms, and the universe becomes transparent. So for neutral atoms, the cross-section for scattering of photons with neutral atoms is very, very small. So the universe actually becomes almost transparent. So from this point onwards, CMB photons are more or less coming straight to us with very little interaction with the intervening matter. There is some interaction. We'll talk about it a little bit, but mostly it is transparent. Right? Which means that the CMB photons, what we see is a picture of the universe as it was at this time when the universe was 380,000 years old. We can know before them. We see the picture of it, but looking at that picture, we can infer what is happening before that also. So there are a lot of dynamics going on, which determines what kind of pattern that we see. And that pattern tells us what is happening a little bit before that also. Yeah. But that is inference. But directly what we see is a picture, just like we see the picture of the wall. This is the photons which last scattered from the wall and then are falling. So this is the point where the photons last scattered and then they are coming straight to us. So it's called the last scattering surface. And this is known as the epoch of recombination. Right. So now we have a plasma. So now I want to maybe switch to Blackboard for a few minutes. Can we turn on this light? Yeah. So before recombination, we have a fully ionized plasma, right, made of electrons, protons, some helium nuclei, and also and photons. There are neutrinos also there in the universe, but they are not interacting with anything in the standard model of cosmology. In standard model of cosmology, there is also dark matter, which is also not interacting with anything else. But the electrons, protons, nuclei, and photons, they are tightly coupled with each other. They behave as a one fluid because they are scattered. Photons and electrons are coupled together by Compton scattering, and then electrons and ions are coupled together by Coulomb scattering. And these scattering rates are high enough that they behave as a one fluid. But this is a very different fluid than any that we observe today. It's a very special fluid because if you go to early enough, you see that the fluid, it is a fluid which is made up of mostly of light. So the energy density of the fluid is dominated by light. The energy density of photons is much, much bigger than even the mass energy density of protons or baryons, nuclei, electrons. And the pressure is, of course, always dominated by light. So it is all, the main source of pressure is the radiation pressure. So light is actually, so it is really a fluid of light. But the baryons are important, or the electrons are important, because electrons is what make this fluid a fluid. Without electrons, the photon-photon interaction cross-section is very, very small. So it will be a collisionless, made up of collisionless particles. So electrons is what makes this fluid, makes it a fluid, the scattering with the electrons, which makes the mean free path of the photons very, very small. So if you look at scales which are bigger than the mean free path of photons, then a fluid, we can use a fluid description or the hydrodynamic description. Right? But the pressure is given by the radiation pressure. So it is a relativistic fluid. At some point close to the recombination, the energy density in baryons or protons, nuclei, and photons, they become comparable, but the pressure is still dominated by photon pressure or radiation pressure. The thermal pressure of the due to Coulomb scattering of electrons and nuclei, that is actually completely negligible. So now the universe, so it turns out we observe again from the CMB and of other observations, universe is very homogeneous and isotropic. And early universe is even more so, but it is not fully 100% homogeneous and isotropic. There are small perturbations. You know, if you put small perturbations in a fluid, then you create sound waves, right? That is how I create sound waves. I make perturbations in the fluid and they propagate. But the sound waves that we create, so these are traveling waves that I am speaking now, and they are coming to you. But the sound waves which are present in the early universe, they are actually standing sound waves. And whether it is standing or traveling, it is determined by the boundary conditions. So the boundary conditions or the initial conditions are such that the sound waves that are set up, the initial perturbations which are present, they start oscillating whenever the wavelength is of order of causal horizon, or whenever the causal, I will come to the causal horizon in a minute. So we have standing sound waves. So what does that mean? That if you look at one particular wavelength, let us say, one particular mode. So we do Fourier analysis because this is linear, perturbations are small. So linear theory is valid. So we can do a Fourier analysis. So if you look at this is X position, let us say we look at one particular mode of wavelength lambda, right? So the wave number 2 pi over lambda. So it will be oscillating. It is oscillating as a cosine wave, and the oscillation part is the temporal part is omega times time. So time I am calling eta is the time, omega is the frequency, right? And frequency is related to the wave number by the sound speed Cs. And because this is a sound speed is determined by the radiation pressure, it is actually relativistic. So Cs in units of C is actually 1 over square root of 3. That is very close to 1. That's as the time passes. So if you look at one particular wave mode, the time t equal to, it is a basically cosine wave, cosine mode which is excited. Again, that is determined by the what is the initial conditions. So as the time passes, so this is eta equal to 0. You start with some amplitude, and then it behaves as temporal part behaves as omega eta, which means that the pattern remains fixed, but it just the amplitude varies. Right? So this I am plotting a density. There will be a corresponding velocity part for the sound waves, which will be out of phase with the density by 90 degrees. So velocity will behave like a sine. So as you go, so if it is a little bit later, it will be something like this. The amplitude will decrease. If you go even later, at omega eta equal to pi by 2, this becomes density perturbation becomes 0, right? And then it reverses direction, right? And then it again. So it's a standing wave, which is the pattern remains the same, but it is oscillating in time. Right. So now we want to understand the nature of these sound waves and how do they behave. So let us see. Next. So this temporal part, or the so this is the what I have written here is the equation. So theta 0 is like the density or the amplitude of this wave, right? And what I have plotted is the equation for this amplitude for different modes k or particular Fourier mode k. This is the equation which determines the temporal variation of the amplitude. Sorry?
What kind of wave is this?
This is sound wave. This is the usual sound wave. This is the longitudinal wave.
This is a longitudinal compressional wave.
Compression wave, yeah. The normal sound wave that is a usual sound wave. It's just the fluid is different. It is actually a sound wave. Right. Okay. So this is the equation which determines how the amplitude behaves in time. Right. This is eta is the time, the second order differential equation in time. And actually, everyone knows the solutions to this equation. This is the standard oscillator equation that appears everywhere in physics. Right. So this part, right. So if you ignore this red part and this dark part, this is just a standard oscillator equation. The solution is this cosine omega eta. Right. This is the right hand side is the forcing term, some external force which is being applied, and this is a damping term. And damping term is coming because the parameters of the fluid is evolving as the universe is expanding. The fluid is actually becoming heavier and heavier. The energy density of baryons is becoming bigger compared to the energy density of photons. So that is this factor R is basically the ratio of baryon to photon energy density. Right? And actually, everyone knows the solutions to these equations, even if you are not a physicist or you have not seen these equations. Everyone who has, played on a swing. Sorry? Yeah, so CS is also a function of time. Here I am assuming the sound speed is also a function of time. So I will come to that in a few minutes. Right? So anyway, we all have played on swing as a child. Right? So all oscillations have the same physics. They are governed by the same similar equations, whether it is sound waves or child on a swing. Eta is my time, yes. Eta is time. Yeah, so eta is time. Right. So suppose you are. Let me try to draw a picture. Maybe let me just draw a pendulum. So suppose pendulum is a child on a swing, and you have a friend which is pushing you periodically. Right. So if your friend pushes you at the same frequency at which the natural frequency of the swing, then your amplitude increases, right? So that is basically resonance. So that is what happens if F, the forcing term, has the same frequency as but the swing, if your friend stops pushing you, then slowly amplitude will decrease and the swing will come to a stop. That is because of the friction. And that is basically what this middle term does. Right? So, sorry? Yeah, so there are parameters of the oscillator are varying with time, and there are also other forcing terms here, right? So I will. So this is not very important. This is just damps the this damping term just damps the oscillations a little bit, but nothing much more too interesting happens here. But the more interesting term is this F term. This is the forcing term, and this force is coming from gravity because so this is a pressure wave, right? So even without gravity, you will have sound waves. Sound waves don't need gravity to act. But because gravity is present, we are on a scale where gravity is actually important. And everything exerts gravity. Everything which has energy will have a gravitational effect, which means that baryons and photons, they have gravity. When you compress the baryons and photons and baryons, their gravity increases, right? So which will try to make it compress even more. So the gravity of baryons and photons, it is like a resonant forcing term. It is like a friend pushing you a little bit further, trying to increase your amplitude. Dark matter is present in the early universe, but dark matter is not coupled to anything. It is just sitting there. So where there is a overdensity of dark matter, it will remain an overdensity. Where there is underdensity, it will remain an underdensity. So dark matter is like a constant force here. So if you apply a constant force to a swing, so the gravity, normally gravity is in this direction. If your friend applies a constant force always in this direction, what it will do, it will change the zero of your oscillations. Instead of the center point being vertical, it will become somewhere where this sum of this force is pointing. And you will change the, you will offset the zero, so we will be oscillating around a different point. So that is what dark matter does. It shifts the 0 point of the oscillations. The, gravity, no, so it is, so everything is evolving little bit. Yeah, so it is eta dependent. So for baryon and photons, it is of course, baryons and photons are oscillating, so the gravitational force is also oscillating. So that is what is giving you this resonance effect. But dark matter is slow, evolving very, very slowly. It is still, there is some time dependence, but it is very slow. So we can approximate it as approximately constant. So then it is just giving you a phase shift. Neutrinos do something very interesting. So let me, right. So this is just what I'm talking about. So if there's no friction or force, then you just have these oscillations, purely harmonic oscillations. Baryons give you a resonant forcing term. Then if you have dark matter, then you get there's a shift in the zero of the oscillations. So I will come to that in a that plot in a little bit. Let me just also tell you about neutrinos. So neutrinos do something very interesting. So neutrinos, initially they are perturbations, density perturbations in neutrinos also. So initial conditions are such that the density perturbation in all components of the universe are same. So the baryons have density perturbations. They initially present. The same perturbations are there in photons, in neutrinos, in dark matter. But neutrinos, as soon as the horizon size or the time since the Big Bang until a particular time, that time becomes of order of this distance scale lambda, so that neutrinos can travel from one part to the other. The perturbations in neutrinos get erased away. This is called free streaming. And neutrinos are traveling at the speed of light, which is faster than the sound speed. So neutrinos, they act like dark matter initially, so they provide a constant force, but at some point that perturbations get erased away because neutrinos are free streaming. So neutrinos from here are moving here, filling up these underdensities. So they are all basically moving around until the perturbations get averaged out. So the forcing term for the neutrinos is like a step function. So initially you have some constant force like dark matter, but then it goes away. So if you have this kind of a force, it is like your friend is pushing you for a little time, but then it goes away. So what it will do is it will just change the phase shift. It will just take the just shift the oscillations in time in a little bit. It just provides a phase shift. Instead of coming at 0 at particular time, you will come at a different time because your friend had given you a little bit of a push. So neutrinos give a phase shift to it. You see that this qualitatively, these different components of the universe which are present at that time, dark matter, baryons, and neutrinos, and photons, they have actually qualitatively different effect on these oscillations, right? And what we see is a combined effect of all those three, but we can disentangle them. And if we can disentangle these effects, we can actually find out how much dark matter is present. It will be proportional. The shift will be proportional to how much dark matter is present. This amplification will be proportional to how much baryons are present. And neutrinos will tell you how much the phase shift that you will get. So it is possible to actually learn a lot by studying just these oscillations, because qualitatively these are very different. In particular, you can see that no matter how much you modify gravity, you cannot get a constant shift without dark matter. Right? Even if you, so people, there are, you hear about theories of modified gravity where you are to replace dark matter with modification of gravity. But no matter what you do, the effect of gravity, modification of gravity will just change the amplitude of these oscillations. But they cannot give you a zero shift. Zero shift, you need something which is completely decoupled from the oscillations. Now we see that zero shift. So that is actually unequivocal evidence that there is actually dark matter. You cannot actually replace dark matter with gravity. And neutrinos do something even more interesting. So now I was talking about this. I drew a particular mode, and so I drew how it will change with time. But now let us look at just the time part, this cosine omega eta. Right. So now I will fix the time. So I fix time equal to the time of recombination or the last scattering surface. Right. So if we, and this is basically cosine of k eta cs. Right. So if you look at different k modes, if I fix eta star particular time, then different modes will actually be going through a different phase at a particular time. Right. Because they are all oscillating with different frequencies. So if we look at a particular time, some modes are going through their maximum, some modes will be going through the zero, some will actually be going through the other minimum. Right. And now when I make the power spectrum or the spectrum of this, I square this. So which means that the minimum and the maximum, they both appear as a maximum in the power spectrum. So that is what I have plotted here. So if there is no dark matter, we have no asymmetry. We have this wave, you square this, we get the power spectrum, which should look like this. And all peaks should have approximately the same amplitude. If I add dark matter, then it shifts the zero. So when you square this, you see that the odd and even peaks, they should have a higher and lower amplitude alternatively. And this is what we see actually very clearly in the CMB data. Right, and this I talked about. So neutrinos actually give you a sorry. Oh, so here the x-axis, sorry. So here the x-axis is k. So the x-axis is k. I am plotting now this. I am fixing the time. And I am plotting what is the amplitude of different k modes. Yeah, sorry, I should have put k here. So the x-axis is k, and the y-axis is the amplitude. You see the different k modes. This will be for k modes for which this is equal to 0 or pi or multiple of pi. We will have a maximum. When it is pi by 2, then or multiple of odd multiple of pi by 2, then you will have a 0, and you have odd. Sorry.
Hearing the sound, all these codes on my, I'm hearing a white noise.
It is not white noise. So this is a pattern. So there is one feature which is very prominent. So I will show you the spectrum in a little while. So initially, to start with, it was a white noise, but then you have set up this sound oscillations and all this physics, and then it actually become very different from a white noise. I will show you a picture. Yes, yeah. So it all depends on initial conditions. So the initial conditions are white noise, that initially all modes have the same amplitude. So then what I'm plotting here are the transfer functions. But it turns out that initially also, in reality also, this is almost scale invariant, the initial conditions. Yeah. Yeah, so already talked about. So what neutrino do, they add a phase shift to it, to these oscillations. Right? And so these are real also, as you mentioned earlier. So sound speed is also a function of time, because the nature of this plasma is changing. So what is comes here? So this is the roughly what it is, but more precisely, it is k times rs, where rs is the sound horizon. So this is the sound speed integrating from 0 up to time, whatever time we are looking at it. So this is the distance which the sound wave can travel up to some time eta. So this is called the sound horizon, and this is the pattern that we see. So we see basically the signature of the sound horizon scale in the CMB spectrum. The peaks will be on scales of sound horizon and its multiples. Right. So we observe this pattern as it exists at the time of recombination. So I told you that from CMB we know how we know about dark matter. Okay, I am almost out of time. I've not even gotten to the results. Okay, so I will try to go a little bit faster. I think I underestimated how fast I will go. So I told you that we know about dark matter. We also know about dark energy from CMB because this is the particular scale which is imprinted in the CMB RS. This is the physical scale, right? So we know the physical scale which exists at the time of recombination, and we know what angle that we measure. We see that scale at some particular angular observe it at particular angular scale today, which means that it tells you how far it is. So there is a small angle formula. We know what is that distance, right? And this distance is the distance traveled by the photons, and it depends on the expansion history of the universe. So distance, we basically integrate over the expanding universe to get what is the angular diameter distance, what it is today. And it turns out that without dark energy, we cannot actually reconcile this. So if there was no dark energy, then we will see the peaks at a different angular scale than what we see. To reconcile that, what we see at a particular, these peaks of the CMB at a particular angular scale with this theoretical model, we need dark energy. So just from CMB, there is actually evidence for it. We cannot fit CMB data without dark energy. And that comes from, so CMB, these peaks, they act as a standard ruler. I talked about standard candle earlier. Right. So this is all three dimensions, but we observe is a two-dimensional projection. So I will just skip over this technical detail. So to project a three-dimensional sound waves into a two-dimensional observational sphere, we have to do a projection that is done by the spherical Bessel functions. Then this is distance to the last scattering surface. So this redshift is around 1100. So scale factor was 10 to the minus 3 when the recombination happened. Right, and the spherical Bessel functions, they project these k modes to the L modes, where we decompose this sphere on a spherical harmonics with the orbital angular momentum numbers. So eta 0 is the time today, eta star is the time at that time. So dA is the distance from here to the last scattering surface. So this Bessel function peaks when L is approximately k times d. Right. So this is the picture that we see, observe the pattern on the sky. I have shown you a three-dimensional version of the same data in the title slide. Right, so you do a spherical harmonic transform of the sky, and we look at these angular frequencies L, and what we see is this. We see that one particular peak is very, very prominent, and then the others are, so you see an odd even pattern. There's also an exponential decay, which I did not have time to talk about because the perfect, this plasma is not perfect. There is a viscosity and thermal conductivity in there, which dissipates the modes on small scale. So there is dissipation. The small scale sound waves get dissipated. So that is why there is the exponential decay on this. If you remove that exponential decay, you see that there is an odd even pattern here, which is the signature of dark matter. And the one peak, which is the first peak, is the most prominent one, which happens around a degree scale. So that is what we saw in the first slide.
Very prominent.
Yeah. So here, because yeah, so they become less dominant because there is also exponential decay, which takes over. So the power is decreasing, but it is actually there. So if you do analyze it very carefully, you see that I think we have now evidence for 7th or 8th peak, which are measured with quite significance. 1, 2, 3, yeah, 6, 7 peaks. Yeah.
So when you say the neutrinos shift the phase, all the modes get shifted equally, or is it scale?
Yeah, so there is a scale dependence in the phase shift. I will
Yes.
come to that in a
Sure, thanks.
one slide. So let me just go quickly. Right, so the acoustic peaks correspond to the extrema of this cosine function, right? Which means that this L peak is approximately k times dA. So we can do a little small calculation. So the peak, the first peak, which will happen, which will be at m equal to 1. Right, so it depends on this phase shift where this peak will happen. If you just look at the first peak, well, it's true for all peaks. So this is the formula which tells you how much phase shift is given by. So the dA depends on the expansion history from recombination until today. This R star is the sound horizon, so it depends on the expansion history from time t equal to 0 until recombination. We have divided it divides it into two. So this peak depends on the ratio of these two distances. So now there is I told you initially there is a tension, there is some discrete debate right now about how fast the universe is expanding. So by measuring these peaks, we can actually measure, there is one parameter which comes out is the expansion rate today, H0. And we can measure this H0 from CMB. We are assuming some model. So here we assume lambda CDM model where dark energy is given by a cosmological constant. Dark matter does not interact with anything. And we measure that the Hubble constant should be 67. This is a 1% measurement, right? But we also can measure directly the expansion of the universe, just like Hubble did. And this was done by many people, in particular, Reese et al. Is one of the groups, and Wendy Friedman is another group. She had given a Madan Lal Mehta lecture a few years ago. So they measure this 74 kilometer per second per megaparsec. So now there is a problem. This is out 4, or now actually, depending on which data set you take, it can also be 5 sigma or even more. So now this is a problem, which means that something is wrong. So either we have discovered something new about our universe, which means that the lambda CDM model is not correct. Maybe dark energy is not a cosmological constant, or one other possibility is that dark matter is not completely non-interacting that we had assumed. It can do something more complicated. Or maybe there is some systematics in the measurements, in our calibration of these local measurements. So the jury is still out, and the only way to settle this debate is by having more data, and in particular, getting more different ways. So this measurement also relies on the same Cepheid variables that Hubble was using. And there are questions about there are systematics in these measurements of the Cepheid variable stars. But there are other methods, new methods now to measure the same distances. And Friedman had talked about that in her Madan Lal Mehta lecture. But again, but the other methods, the error bars are still not good enough to resolve this. So other methods, they are consistent with both. Their error bars are big enough. So their value lies somewhere in between, and the error bars are consistent with both measurements. So, but we have to wait, I think, a little bit to find out which one will be true. But assuming that this is actually a new physics, that both of these measurements are correct, so then we can try to figure out, okay, what kind of new physics you need in order to reconcile this. And the idea that we came up with was, so CMB measures this, all these density, omegas are the density, how much dark energy density is there, how much matter density, how much radiation density. So these are actually quite well measured. We cannot change these. So if you try to increase the Hubble constant, so local measurements want the Hubble constant to be slightly larger, right? And keeping these things constant, you find out that basically what you need is to make the Hubble parameter, you have to add a constant factor to the Hubble expansion rate all the way from today until time t equal to 0. But the universe is a decelerating universe. Early times, the universe was expanding faster. Today, it is expanding slower and slower until very recently when it started accelerating again because of dark energy. But earlier there was no dark energy, so it was a decelerating universe. So earlier the expansion rate was much larger. Today it is much smaller. So if you add a constant factor to the expansion rate, then earlier it becomes unimportant. Right? It only affects the late time expansion history, where it is important compared. This term is important compared to this term only in the late times. So people have tried to. So if you just increase the Hubble, what you see is that in CMB, if you make the Hubble constant larger, it will shift the peaks. it will change this angular diameter distance to the CMB that we will measure should be different. So the peak should be at a different place than what we observe. So there is a discrepancy in where the peaks should lie. So if we can move the peaks back to the original place, then we will have solved this. So one way to do this is people have tried to change dA or R star. That runs into some problems. But we came up with the idea that there's actually a phase shift. So the peak position depends on dA, R star, or phi. So you can modify dA in order to reconcile these. You can modify R star from the standard history, or you can modify this phi. So we realized that actually this phase shift is coming because neutrinos are free streaming. They don't interact with anything. But if you make neutrinos interact with a small fraction of dark matter, so that you stop them from free streaming, so that their mean free path becomes much, much small, just like photons. They are not able to move freely about, and this phase shift goes away. If this phase shift goes away, then actually the Hubble parameter that you measure from CMB, it will agree with what we measure locally. So that solves the discrepancy. So I'll just go a little bit. So this is the phase shift that you require. Right, so running out of time, so I'll just go. So this is showing you what happens. So this red curve is the lambda CDM curve that we measure from CMB, 67.9. If you make the neutrinos interact with dark matter, if you stop the neutrinos from free streaming, you remove that phase shift, then this curve will shift to this blue curve with the same Hubble parameter constant. But this is what we measure. These are the points what we measure. So to bring it back to the measurements, we have to increase the Hubble constant. So if you remove the phase shift and you have to increase the Hubble constant, then you again agree with the data, and then you agree with the local measurements. So this is the solution. So again, you can do a more complicated MCMC analysis, and you show that this Hubble constant is with this, when you introduce the interaction for neutrinos, it increases.
It's only 5% change you introduced, right? There's a 10% change in the numbers, 74 and 66.
Yeah, so but you also increase the error bar a little bit, and then you reconcile this. Yeah, so we don't actually go to the 74 central value, but I increase the central value to, so this is basically the error bar. If you look at this blue curve, basically they agree within 2.2 sigma. So these horizontal bands are the local measurement with the error bars. And this blue curve is the one of the, or this red curve, if you look at it, you see that they agree within 2 sigma. So the discrepancy instead of 4 or 5 sigma, it becomes 2 sigma, and that can be a statistical fluctuation. So it depends on how seriously. In actual measurements, you cannot really match the exact value of central value to central value. That would be a conspiracy if you. And there's a prediction for this. So you should see signature of this neutrino interactions in the matter power spectrum also. And that is a way to test this model. So we may have discovered a new interaction of neutrinos. So if you give me a few minutes, I will just maybe just say a few words about the other part of the talk. So I talked about the CMB spectrum. And we COBE measured the CMB spectrum. It is an almost perfect black body. And it is actually black body at a level of 1 part in 10 to the minus 4. So it's the most perfect black body that we know, or even we can make in the lab at that time. So most of the error comes because of how perfect a black body they could make to compare the sky, calibrate the sky. So most of the error, if they could have made a more better, so this experimental sensitivity was much bigger than this. But it was just the errors in the black body that they could make in order to calibrate experimental black body that actually introduces this main source of this error. So now it turns out that at redshift or greater than 10 to the 6, the universe is actually in perfect equilibrium, and any deviation that you create in the CMB spectrum from equilibrium, it is exponentially suppressed. But below 10 to the 6, these processes which can create this equilibrium, they actually become inefficient. The rate becomes much smaller, or the time scale becomes larger than the age of the universe. There's not enough time to equilibrate. So at that time, if you create a deviation from equilibrium, disturb the equilibrium, that disturbance remains. And that is what we call the spectral distortions. And one of the thing is particle cascades. If you have some short-lived, so dark matter is a stable new particle beyond standard model that we think exists. But there may be some dark sector can be, dark matter may not be as simple as just one particle. Standard model is very complicated with many particles. Many are stable, many are unstable. So there may be new unstable particles which decay before recombination. So we don't see them today, but they will leave their imprint because they will disturb the equilibrium. They are adding some new energy and new particles, new electrons, higher energetic electrons, which will scatter the CMB photons. So they will create these spectral distortions in the CMB, deviations from the CMB, which can, in principle, we can see in the future. Again, so these are also the primordial black holes. People think they are quite in fashion now. So they evaporate by Hawking evaporation and also inject energetic particles into the universe. They will also disturb the equilibrium that CMB has, the equilibrium spectrum. And again, you can put constraints on how many, so this is the density of black holes, basically this parameter, how much black holes are allowed of different masses. Also, you can have a dark matter may not be a fundamental particle, it may be composite particle like neutron, or it can be overall neutral, but maybe made up of charged constituents like hydrogen atom or neutron or a proton. And then, which means that it can have internal electromagnetic interactions. So it can absorb the CMB photons which are coming if this transition is right. So it can also introduce some, again, very interesting features in the CMB spectrum. So that is another possibility that we can look for in future. In particular, there was recently this experiment which actually did detect anomaly in the CMB spectrum in the far Rayleigh jeans detail. And this composite dark matter model can explain this anomaly. And also there are free electrons in the, I told you universe recombines, but at some point first stars form, they reionize the universe again. In particular, the galaxies don't live in isolation. A lot of galaxies are in clusters of galaxies. And these clusters of the medium between the galaxies is highly ionized, fully ionized plasma, just like the early universe. So CMB photons will again scatter on these electrons, and they leave imprint in the CMB. And one particular imprint is basically the peculiar velocity. The clusters are moving with some velocity with respect to each other. So close by clusters will be falling towards each other. So this velocity will introduce Doppler effects, relativistic and usual Doppler effects in the CMB radiation. And we can actually measure the signatures of these Doppler effects. And that can tell you the velocity fields in the universe, how the different things are moving in the universe. And that has interesting applications. In particular, we can learn about dark energy or the gravity, test gravity on large scales using these kind of observations. So this is one plot which shows that what happened. So this is a recent work. So earlier people were using some methods to analyze this kind of data, which was giving you error bars, which are these outer circles. But we have proposed a new method. Basically, they were correlating clusters with clusters, but we are correlating clusters with galaxies. It turns out to be slightly more efficient. And with our new method, we can actually, with the same data, we can actually do much better. We propose new methods to analyze data, which should be interesting in the near future, hopefully. So of course, all of this work that I have told you about, this is done by hard work. All the hard work is done by the students. I have shown this very quickly. Shubhajit's work a little bit more detailed, but other works a little bit more quickly. And in particular, a lot of this work is in collaboration with Tuhin. And we were very lucky, Tuhin and I, that we had students actually who were interested in both particle physics and cosmology. So they are willing to learn both. And this is not an easy task. Usually in a PhD, there's barely enough time to learn one field, but they decided to learn both. And because of them, actually, we were able to explore both sides of these dark matter models in our papers. I have only talked about the cosmology part, in particular Shubhajit and Anoma. So they worked on these papers where they explored collaboration with Tuhin, where did both particle physics and cosmology. So last, I was to come to this first word of my title, Anahata. So I think maybe you will be convinced even if you did not know what it meant before. So Anahata, literal meaning is unstruck sound. So the ordinary sound in the Indian theory of music, ancient theory of music, the sound that we hear is the ahat-nad or the struck sound. But there's also a concept of anahat-nad, which is the unstruck sound. And we think that this sound waves, early sound waves that we see in the CMB, their origin is in quantum spontaneous quantum fluctuations of the vacuum that happened much earlier. So in a way, that is like what I am calling it Anahata. I think it is not a very, it is quite accurate and appropriate name for this primordial sound waves. There's also an interesting book by Sheila Dhar, who was a Hindustani classical vocalist. And you can imagine from the title that she is as interested in food as she is in music. And there are interesting stories in this book about music, musicians, and their relationship with food. So I will highly recommend it if you like food and Hindustani music. It's a very fun book to read. But there are also some essays in this book. And one of the essays, she tries to describe Anahata, and she uses the phrases sound and light are fused, or hum of creation. So for a person working on CMB, it immediately brings to my mind the primordial sound waves. But of course, she is not referring to cosmology when she says this. She's not even referring to the physical world, but she's referring to something else entirely. You can read the essay to find out what she's referring to. And I will just leave this is the final paragraph of this book by Hubble, in which he described his observations of the expansion of the universe. I will just leave this here for you to read. I like this, a very poetic way of putting things. I like this, how he has put different things. I'll just leave this here and stop. Thanks.
Thank you very much, Rishi. Thank you for such an elaborate talk. And yes, questions? We'll have Rajdeep.
So your analysis, of course, used a lot of equations of state, perfect fluid, etc., right? And there would be, in general, errors in assuming those equations of state.
No, so yeah, so this I have shown for explanation, this simple hydrodynamic picture. So it is good approximation in the early universe when everything is very tightly, density is high, and fluid description is accurate. But as the universe expands, the mean free path actually becomes non-negligible, and this description breaks down. And then you look at we solve the full Boltzmann hierarchy.
So what I'm saying is, if you evolve, is that 10% allow, if you, depending on how much your initial conditions change, would you get that 10% out of that? Or do you need to invoke new physics? Because these are two different things, right?
Sorry, what 10%?
So let's say Hubble tension, you had this tension. I'm saying
no,
that.
So here we are assuming that initial conditions are featureless. They are scale invariant. Okay. If you assume that, then you cannot really reconcile that. But of course, you can put arbitrary features in there, but then you are introducing 100 parameters. So of course, you can do arbitrary modification in, then you can fit anything.
So you mentioned about the effect of dark energy on the CMB spectrum. And how does it exactly appear? Because when photons decouple, perhaps dark energy is not as important.
It is not. It appears when the photons travel from them to us. So then at the recombination, there is a physical scale, R star. And then they come to us, they travel some distance, dA, and then we observe them at some angular scale. So the dark energy determines how much distance they are traveling. If there was no dark energy, they would have traveled less distance, so they would appear at a different angular scale than what we see.
In the end of the talk, you mentioned somewhere that earlier universe contracting, now it is expansion.
No. So I was saying that universe is expanding today. So we extrapolate backwards. If you go backward is time, then universe is contracting. Earlier and earlier it is. Yeah. There are models where universe contracts and expands, but we are not talking about those.
Any other questions? If not, let's thank Rishi once again for a very nice we will join Rishi for a bit of snacks and tea. Thank you. I thank the AV team again today for putting it up with Zoom and YouTube.